Hello. In this video, we're going to take a closer look at the normal distribution, or the normal curve, bell curve, as you may call it. First of all, this is a very quick look at the algebra. So this is what the equation for the normal distribution looks like right here. And you'll notice there are three variables in this equation. One is the raw score x. So these, because all distributions are distributions of data. From this data, if it's a measurement variable, we calculate the mean. So we have the mean as one of the, so this is the x, the mean, and then we have the standard deviation. And when it's squared, we call it the variance. Okay, so the normal distribution is a combination of raw scores, means, and standard deviation for that distribution. Visually, we know what the normal distribution looks like. It looks like a bell curve. When we change the value of the mean, mu, in the distribution, we shift the whole curve to the left or to the right. So that's what this bit here does. Changes in the standard deviation, as you can see here, it's in the denominator. What it's going to do is it's going to change the spread. And so you can see that here. When we have standard deviation equals 1, we have the same curve, but with different means. Here we have mean equals 4, here we have mean equals 8. That shifts the distribution to the right as the mean goes up, or if you started with the 8, you'd be shifting it down. As standard deviation changes from 1 to 2, we get kind of a flattening. So you put pressure on this, and you see that these ends actually flare out. So we get a wider spread, higher standard deviation. Kind of makes sense. Here's a closer look at the standard deviation, or different standard deviations for the normal distribution where mean equals 0. So the mean here equals 0. So take a look at that and think about, so what's happening here? Standard deviation is a half. As it increases, there's more spread, and the distribution actually flattens. When we speak of distributions, there's two ways to look at them. We have actual distributions. What does the data have look like? So we know, we look at center, spread, and shape. And then there's theoretical. What model fits the data that I have? And so here's a good picture that kind of gets that idea across. So we have a cat or a kitten, and then we have the model. And as we know that, so the joke here about negative self-image, reality doesn't, or rarely meets kind of the ideal or the model. Statisticians use models to predict things about the world. These models are always based on mathematical equations and functions. And these models are usually, or for statisticians anyway, they're probability distributions. So in our case, they'll be related to frequency distributions. And so these models, these images that you've seen before and you've worked with, are actual, these shapes are models of distributions that we see out there. Here's an example of a uniform distribution. There's one die rolled 36 times. What is expected? So that's the model. What we expect to happen is the model. And we would expect 6 1s, 6 2s, 6 3s, 6 4s, 6 5s, and so on. We would expect to get an equal, if the die is fair, we would expect to get an equal number of each of the possible outcomes. So if we look in probabilistic probabilistic terms, sorry about that, we would get the probability of getting a 1 equals the probability of getting a 2 equals etc., probability of getting a 6, each of which would be 1 and a 6. And so we would get a uniform distribution. And so this is the model for rolling one fair die. The normal distribution is useful in many, many other cases where the uniform is not. So for example, histogram of the weight of 133,000 Canadians from the Canadian Community Health Survey data. This is what it looks like. Is it a normal distribution? Close enough? Sort of like? So we could take this data, the mean here, standard deviation, and create this normal distribution where the mean would be 73.87. So you put 73.87 here, and we would have standard deviation of 17.776. And so we can create a model for the distribution of weight in Canada. Now, you can quibble that there's outliers here, right? And so those make this not a perfect model, but it's close enough. How do we tell if a normal distribution is a good model for a data set? One, is it measurement data? We do numerical exploration, symmetry. We look for symmetry. Is the mean approximately equal to the median, approximately equal to the mode? Visually, is the shape a bell curve? Sort of, right? So we saw the distribution of weight. It's sort of a bell curve. Skewness. We can get a measure. We can get SPSS to produce that for us. Is it close to 0? Kurtosis, is it close to 0? Standardized normal distribution algebraically. So we're shifting from distribution that's rooted in the actual population to a standardized normal distribution. So what we're going to do is we're going to set mu equals 0, sigma equals 1. So you saw that in the beginning. We had slides like that. And if we do that, what we actually have happen is that this is the original function, and this becomes the standardized normal distribution. And so you see what happens here, because mu equals 0, it drops out. This nicely drops out here. And if we set this equal to 1, we end up with these numbers. Very straightforward. Sorry, this becomes 1, this becomes 0. There we go. Characteristics of the standard normal distribution. Symmetry about the mean. We looked at that already. So here's the mean. Mu equals 0. So remember, standardized normal distribution, we set mu equals 0 and sigma equals 1. When we set sigma equal 1, so you can say here this is 1 sigma, 2 sigma, 3 sigma, etc. -1 sigma. So the x-axis is the number of standard deviations. So you're 1 standard deviation below, 2 standard deviation below, 3. And that is why what makes standardization very useful. So we have symmetry about the mean, which means 50% of the data is above the mean, 50% is below. Normally, we can say that about the median, but not necessarily about the mean. So if you add these up and these little bits, you will get 50%. 34.1% is within 1 standard deviation. So let me just change colors here. Ink color, I'll change it to black. Right? So this is 34%. as this indicates, and this is 34%. How do we get that? How do we know it's 34%? Calculus. So with calculus, what we can do is we can calculate under this curve using the algebra. We can calculate the area under this curve. We can estimate it as well with rectangles, and that's essentially what calculus does on a minute. So if we take two of these, we get 68%. So that's where that 34% plus 34% comes from. Next, we look at 95% of the data is within 2 standard deviations. So that's this here, right? So it's this area plus this area plus this area plus this area will give me 95%. So this 2 times 47.7, that's this plus this, red plus blue, and we multiply that by 2 because it's symmetrical. Same thing happens on the left as the right. So these are worth memorizing. There's my heart. There's an applet. I'll be putting a link up. It's not the greatest applet, so it's for those that really would like to play with these things. But it's okay. It takes a little bit of practice getting used to it. But if you want to practice just getting a sense of how the area under the graph is related to number of standard deviations, it would be helpful. Standardized normal curve is created from an actual distribution. How do we create the standardized normal curve? We create it through this little equation. Very simple. Transformation. So we start with a raw score, subtract the mean, divide by standard deviation. And this is for each raw score, right? Each raw score in the distribution. So essentially what we're doing is we're taking each of these raw scores, each of these x's here. We know the mean here is 78. Standard deviation 6.1. So like this is plus 6.1. This is 2 standard deviations, right? Plus 12.2, roughly. So we got that idea. We transform this from a raw score distribution into the standardized. Let me just erase these numbers because they're not useful here. But they're still here, right? So this is still mu equals 70, what was it? 78, I think, right? And here we have plus 6.1 plus 2 times 6.1. Okay, so these are Z scores, which equal number of standard deviations. Okay, it's time to take a breath. And as you take a breath, it'd probably be a good idea for you to try to draw a normal curve with characteristics mu equals 37, sigma equals 4, and outliers at 3.5 and negative 4.2. Sorry, Z. Okay, so that'll give you a sense of whether you understand the basics of the normal distribution. Thank you for watching.